Welcome to video 5 of Engineering 626. Now that we have completed the first two computer projects, which actually involved your writing several computer codes, I believe you probably have a much better idea of what we want to do in this course, and you have an idea of now how you might use numerical methods to solve at least an ordinary differential equation, and you have also seen how error can arise in this solution under certain circumstances. Now in today's video, we want to explore this idea of error a little more closely and to see in a very interesting way to reduce the error. So let's start by making a distinction between local error and global error. Now, so far in your plots, we've primarily been focusing on local error. In other words, as you can see here in this top equation, we've been looking at the difference between the numerical solution and the analytical solution. And we have defined that difference to be the error. So again, that gives us the idea of the error of what we call local error. In other words, that's the error at a single point. But frequently of more interest is the idea of global error, so that it will give us an idea of how much error there is in the entire solution. And the global error is commonly defined as shown here. We have global error is equal to the square root of the summation over all of the nodes. So we're summing from I equals 1 to n. We have n nodes, and at each node what we will do is calculate the difference between the numerical value at that node and the analytical value. The y-ex means y-exact. It's the same thing as the analytical solution. So we have y numerical at that node minus y-exact at that node, and we square that, and then we sum up all of those squared values and divide by n. And then finally we take the square root. Now this is also called the Rms error. And if you think about it for a moment, now you might have initially thought, well, why take the square root and why square all those errors? Why not just sum up all of the errors and then divide by n to get an average error? The only problem with that, I encourage you to think about it for a moment, maybe turn off the video and think about it for a moment. Why don't we do that? Why don't we just take this error, this local error that we have up here in this equation, why don't we just take the local error at each node and sum it up for all the nodes and then divide by n. Instead, what we're doing is we're taking that local error at each node and we square it, and then after we add up all those squares, then we take the average of those squares and then take the square root. Why do we do it that way? Well, you might, as I say, you might turn off the video for a moment, think about it, and then come back. Okay, so I hope that if you thought about that for a moment, you see that the reason we don't calculate the global error by simply taking the average of all the local errors is that then we might get a answer that we could even get a global error of 0, which would lead us to think that we have a very accurate solution when perhaps we have a terrible solution. How could that happen? Well, if we have a local error that is positive in some nodes and negative at other nodes, and we simply took the average of all the local errors, it could average out to 0. And we don't want that to happen and give us the impression that we have a good solution when in fact maybe we don't have a good solution. So that's why we're squaring the local error at each node, so that whether it's positive or negative, it's going to give us a positive contribution to that square, and then we take the average of the squared values and then finally take the square root. So that's how we will define the global error. And please do keep this this equation here for the global error, keep it in mind, because you will want to be using that for our subsequent work. Now, one of the next topics we're going to talk about is Richardson extrapolation. But before we get to the Richardson extrapolation itself, I want to talk about the idea of a convergence study. And this is going to be your next program, is to do a convergence study. So let's read what this says. It says, in a convergence study, you obtain a numerical solution at delta x equals h, and then at delta x equals h over 2, and then at delta x equals h over 4, and dot dot dot. Now actually, let me just say, you don't really have to use those increments. You could just use at different values of h. This is a halving the spacing, or in other words, doubling or roughly doubling the number of nodes each time. This is a very convenient way to do a convergence study, but you don't have to always double it. You could use some other factor. Now, when we get to Richardson extrapolation, we will want to be doubling the number of nodes each time, so that delta is halved with each successive solution. But for convergence, simply for a convergence study, that's not critical. So anyway, let's just assume that you'll be doing that. You'll double n each time, so that the value of delta is halved. In fact, let's actually think about that for a moment. Let's stop here. Okay, the critical issue here is that you want to have delta get halved with each. I mean, once we get to the Richardson extrapolation, we want delta to be halved each time. So this means almost doubling the nodes, but not quite. Let me explain what I mean. So suppose you do one solution. I'll write here in the margin. Suppose you do a first solution with n equals 11. Now, since delta is equal to L over n minus 1, then delta in that case would be equal to L over 10. Now, if you want to half that delta, then what should be your next value of n? Well, it should be 21, because notice that if we take n equals 21, then delta in this case would be L over n minus 1, so delta would be L over 20. And then the next value would be n equals 41. So with each successive solution, we're almost doubling, but not quite doubling the number of nodes. So just keep in mind that, and that will give us the desired halving of delta with each successive solution. Okay? Now, at each spacing, what you will want to do is, it says, we're getting back here to reading this, it says, at each spacing, determine the global error. Then we can plot the global error as a function of the spacing. Now, so that's the first thing I want you to do, is let's actually go ahead and jump ahead here. So I say assignment number 3, but let's actually, this is project, let me call this project 3. And so this is assignment number 1. This is the first part of project number 3. Will be to write a general program to solve d squared y dx squared plus k squared y is equal to 0, with y of 0 equals a and y of L equals b. And so all of you now in project 2, you have written a code very similar to this. You used this same equation, and you use this same boundary condition at the left-hand side, y of 0 is equal to a. The only difference is that at the right-hand side, you use the boundary condition dy dx at L is equal to B. And so now I'm asking you to change it to y of L is equal to B. So you'll write a program to solve that differential equation. And of course, you know by now that by general, what we mean is that you should write your program in such a way that you can easily vary the number of nodes, the value of A, the value of B, the value of L, and the value of K. You should write your program so that all of those can be easily varied at the very beginning of your program. And once you have written that code, then you want to conduct a convergence study. This is part 2 now. You want to conduct a convergence study for your numerical solution. So what I would suggest that you do is you first of all get your code working, and that should be very easy, since this is very easy because this is so similar to your code from project 2 that it should be easy, very easy for you to get this code working for a single value of delta. And then once you have that, then you will want to take your program and put it inside a loop so that you can easily vary delta. In other words, with each successive solution, you'll keep, of course, A and B and K and L. All of those will be the same. The only thing you'll change is change that value of N in the appropriate way with each successive solution so that your value of H is halved each time. And each time, for each different value of H, you want to calculate a new global error and keep track of both H and the global error and how they're related to each other. You know, for each H, you want to record the H, the value of H, and the global error. And then when you get through with the loop, you want to plot the global error as a function of H. And I want you to do actually 2 plots, and these will be on different graphs. Okay? In the first graph, I want you to plot the global error as a function of H. And then in the second graph, I want you to plot the, let's see here, let me check and make sure. Let's see. Remember, to help you understand what I'm about to say, okay, we have the global error is approximately equal here. I mean, it has higher order terms to alpha H squared, where alpha is some constant. Okay? And so we know what that first graph that you have, that when you plot the graph, or when you plot a graph of the global error versus H, it should be looking like a parabola. But to really help us see how things are working, so that will be the first graph, and then the second graph, take the logarithm of each side of this equation, and we will get log of alpha plus 2 log of H. So I want you in the second graph to plot the log of the global error versus the log of H, and you should get a straight line of slope 2. So plot both of those plots, and that will conclude the first part of project 3. Okay, before I proceed, I'm being a little sloppy with my terminology, so let me correct something here. I've been using delta as the spacing rather than H, so let me come back up here and make this H a delta, and similarly down here I'll make that a delta. And we will think of H as being some fixed value in our later discussion, but delta is a variable value. The delta will be the spacing between consecutive nodes, and it will be something that we can vary, and h we will think of as being our initial value of delta. So just to repeat then, we will start off our convergence study with delta equal to h, and then we'll go to delta equals h over 2, delta equals h over 4, delta equals h over 8, delta equals h over 16, etc. So think of delta as being variable and h as being the fixed value of the initial spacing in your mesh. And so in the first part of project 3, we want to do this equation right here with these boundary conditions, and we want to write the program to be general, and we're going to, once we have that program working, then you're going to put that whole program inside a loop that will allow you to pick an initial value of h, or and that's the permanent value for h again, because h is a constant, and the initial value for delta will be equal to h. And then as we go through as we loop through this program, each time we will cut delta in half, and that will, in each case, will calculate the global error, and that will allow us to do this first graph up here, which is a plot of the global error as a function of delta. And then in the second graph, we want to plot the log of the global error as a function of the log of delta. And in the first plot should be a parabola, and the second plot should be a straight line of slope 2. So that is the first part of project 3. Now all of that is in preparation for the next part, which is something called the Richardson Extrapolation. And so let's go back to understand what the Richardson Extrapolation is. So here we, scrolling back in the lecture notes, we have Richardson Extrapolation, and we have discussed that first paragraph. And now let's go into this second paragraph. So it says, since we found that our derivative formulas are second order accurate, we expect that this might also be true of our overall solution. And so a way to put that in terms of an equation is shown right here. We say that y numerical, y num of x and h, now that is supposed to denote the numerical solution at location x when the value of delta is equal to h. Okay, that since this is second order accurate, that is going to be equal to yex. Remember, yex is the exact answer plus c times h squared. So the error, now we also have higher order terms, but we're not going to worry about those higher order terms here. We're going to look at the leading term of the error, which is c times h squared, and h is that is the initial value of our spacing. Okay. Now, if we went to actually propose here a value of 2h, but that's not really very helpful. I mean, what I have here in the notes is not incorrect, but it's not quite as helpful as I would want it to be. So let's just correct that right now. So we originally do a spacing of h, and then we want to go to a spacing of h over 2. So let's do that. So we'll say y of x comma h over 2, and to calculate this, we just substitute h over 2 in the above equation where we have h. So we'll now have h over 2, and that's going to get squared. And of course, that will be h squared over 4. So let's, when we again, when we square out this h over 2, that'll give us h squared over 4. And so I'll just put down here c over 4 times h squared. Okay. Now the idea is that we want to add together a certain amount times this first equation plus a certain amount times the second equation, so that we cancel out that leading term in the error. And so you'll see that if we took y numerical, okay, let's take the first one, y numerical of x comma h, and if we subtracted from that, so we're going to subtract from that 4 times y numerical of x comma h over 2. And again, what I had before was not wrong, but it's just, I think that this will be more helpful to you. Okay, so we're going to subtract from that 4 times y numerical of x comma h over 2. So we're basically just taking this first equation up here and subtracting from it 4 times the second equation. And so if we're going to do that on the left-hand side, then we have to do it on the right-hand side as well. And so on the right-hand side, we will get negative 3 times y ex of x. And then we get higher order terms in the top and higher order terms in the bottom, which just group all together to higher order terms. Okay? And now, if we do a little bit of algebra, let's see what we'll get. We take the higher order terms over to the other side of the equation and then divide by negative 3, and so this will give us 4 times y numerical of h comma x over 2 minus y numerical of x comma h divided by 3 minus higher order terms. And if you wanted to be picky, you could say higher order terms divided by 3, but that's not important. Don't really worry about this term. This is our formula then for the exact solution. It says that the exact solution is 4 times our numerical solution obtained with spacing h over 2 minus 1 times the numerical solution obtained with delta equals h divided by 3, and then plus we have error. So basically what this is saying is that if we, instead of taking just one solution, we're now taking a linear combination of 2 solutions. And by doing that, then the error is of a higher order. We have canceled out the second order part of the error, and now our complete error, in other words, you might look at it like this: the only difference between the exact solution and this Richardson Extrapolate formula, the difference between the left-hand side and the right-hand side now, it no longer involves second order terms in h, but only higher order terms. And so this should be more accurate than what we had before, where our error contained a term that was second order in h. Now our error, you see, this is the error now, and the error now is a higher order in h. So that's our idea, is that if we now of course there is some cost associated with this. We have to calculate 2 solutions. We have to calculate with delta equal to h, and then we have to calculate with delta equal to h over 2, and then we have to combine those 2 solutions using this formula. We have to take 4 times that second solution when delta is equal to h over 2, subtract from it the solution we obtained when delta was equal to h, and then divide by 3. But if we will do that to get a brand new solution, that brand new solution we hope, will be more accurate than either one of the two solutions that we have generated at, either delta equals h or delta equals h over 2. That's the whole idea of the Richardson Extrapolate method, and it's really quite interesting the way that works. So we can skip over this part, and now the next part of project 3 will be to do the Richardson Extrapolate. And when you do the Richardson Extrapolate, I want you to again produce these two graphs of the global error as a function of delta. Now it will no longer be delta squared, but just produce global error as a function of delta, and the log of global error is a function of log of delta. So let me go to a different page now and summarize all this for you. Okay, so let's come over here and we'll say project 3, and let's see what we have. Okay. So, part 1, write a code to conduct a convergence study for the finite difference solution of d squared y dx squared plus k squared y of x equals 0. Y of 0 equals a, y of L equals b, number of nodes equals n, and delta equals L over n minus 1. And I'll put in the word general up here as usual to signify that you should write your program in such a way that A and B and L are variable, and obviously n will have to be variable because it is by varying n that you get to vary delta, and of course varying delta is necessary in order to conduct a convergence study. So obviously you must make it so that n is variable. And then the two things that I want you to do will be to produce a curve or graph of of global error versus delta, and then B, produce a graph of log of global error versus log of delta. So that's part 1 of project 3. And now for part 2, write a code to solve this same equation using the Richardson extrapolation method. Now let me say a little more about that. You should be able, for part 2, you should be able to use your code from part 1 as the starting point. And so let's talk about this, and you will need to pay special attention now because this is just a little bit complicated, so listen carefully. Okay, in part 1, as we said before, you're going to have a loop. And what this loop will do is at the beginning of the loop, you will set your value of delta. Now, the way you do this is by setting the number of nodes, because again, delta is equal to L divided by n minus 1. So by picking your value of n, you are in effect choosing your value of delta. And the first time through the loop, you'll choose delta is equal to sum h. Then the second time through the loop, you will choose n so that delta is equal to h over 2. And then the next time through the loop, you'll choose n so that delta is equal to h over 4. And next time through the loop, choose n so that delta is equal to h over 8, and so on. So that's the way that you would do part 1 of the code. And for each different delta, you want to calculate the global error, and then you will, in the end, plot the global error versus delta and the log of the global error versus log of delta, and those will be two separate graphs. Okay, now for part 2, what do you do? Well, again, you're gonna start with this code from part 1. That is, you're going to make a code that will loop, and each time it loops through, it goes through the loop, it will cut delta in half. It starts with delta equals h, and then delta equals h over 2, delta equals h over 4, delta equals h over 8, etc. The only difference now is that for each value of h, excuse me, let me start. For each value of delta, you're going to have to now generate 2 solutions rather than just one solution. Because, see, the Richardson extrapolation formula, again, from our previous notes, the Richardson extrapolate formula that we looked at right here, it involves a solution calculated at 2 different values of delta, at h and at h over 2. Or similarly, you can think of it as one value of delta and then another value that's half that amount. So in this code, when if you think of it now about using your code from part 1 as the starting point, okay, the first time through the loop, you're going to set delta equal to h, and you'll get 2 solutions now. You're going to have to solve the problem twice. You'll solve it once for delta equals h, once for delta equals h over 2, and then you will calculate a Richardson extrapolate solution. Let's come back over here. Let's you'll calculate this Richardson extrapolate solution. Well, maybe in fact let's call that YRE of x. That's equal to 4 times y numerical of x, h over 2, minus 1 times y numerical of x over 8, x comma h divided by 3. So let's actually repeat that formula over here. So we have YRE of x is equal to 4 times y numerical of x comma h over 2 minus 1 times y numerical of x comma h divided by 3. And actually, rather than h over 2 and h, let's use delta so that you understand this is going to be valid. This is what you're going to use for any value of delta regardless. So delta over 2 and delta. So for each delta, the first time through, delta is equal to h. The second time through the loop, delta is equal to h over 2. The third time through the loop, it's h over 8. And then the fourth time is h over 16. Each time through the loop, you're going to cut delta in 2. But don't get this confused, because each time through the loop, you actually want to calculate 2 solutions. You're going to calculate it with whatever your current value of delta is, and also calculate it with half of that delta. And then you will combine those 2 solutions, as is shown right here in this formula, to get a third term, or a third value, third solution, which we're calling YRE. That's the Richardson Extrapolate. And then once you get RE, so once you find y sub RE of x, find the global error in y RE of x. Then, as before, you will plot plot global error versus delta, and B, plot log of the global error versus log of delta. And I hope that this will be very interesting to you, because you'll see that these plots will look different now, because the global error is differing, is a different function of delta from what it was, from what you will have observed in part 1, because of the fact that the Richardson extrapolation, or the Richardson extrapolate, doesn't contain those second order terms. It only contains, the error in it only contains higher order terms. Now we will see that reflected in the shape of these graphs. But there's one trick here that you need to be careful to notice. And let me, so I'll say be aware. Okay. Let's say that you're at some stage in this process in the looping process where your mesh looks like this. And so you will calculate your y numerical. Remember, at each step you need to calculate 2 y numericals. And so you're at the stage where delta is as shown here. Delta, all these are delta. And then you're going to, in the same step now, before you go to the next value, the loop variable, you're going to remember at each value of delta, you actually now have to calculate 2 solutions. One is obtained with the delta at that stage, and then for the other one you're going to cut delta in 2. So I'll put in that. What is cutting delta in 2? That means putting in some more nodes. So if you're going to now use a new delta that is half of your current delta, then you'll need to put in another point here, another node here, another one here, 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 and here, so that now your new delta will be half of that of the previous amount, and you'll need to calculate your new solution. But then the critical thing is, as we said just right up here, you will need to take a linear combination of those two solutions that you have just obtained. Now think about that for a moment. The solution that you obtain spacing delta, you will obtain values only at these solid circles, because those are the only nodes you have in calculating that solution. But when you calculate the solution with 1/2 delta, you will get values not only at those solid circles, but also at the x locations. So when you then want to take a linear combination of the two solutions, how can you find out what this is? 4 times y numerical of x comma delta over 2 minus y numerical of x comma delta. Okay, you can only evaluate that at places where both solutions are defined. What I'm saying is that your original solution with spacing delta is not even calculated at these points labeled x, right? It's only calculated at the locations with the solid circles. Now the solution that you calculate with spacing delta over 2 is defined at both the x's and the circles. But the solution that you calculate with the original spacing of delta is only defined at the circles. And so there's two ways that you could solve this problem. You could use linear interpolation to figure out what that original solution would be at the midpoints. But I think an easier way is just when you go to calculate the Richardson extrapolate, and in fact this is not just easier, but I think this is the best thing to do. In fact, let's say it's definitely the thing to do, because we're going to, when we plot the Richardson extrapolate as a function of delta, we want to use that original delta. So in other words, what I want you to do is calculate YRE of x only at the nodes in the mesh with spacing delta. In other words, don't worry about trying to calculate the Richardson extrapolate at those locations marked x, because you don't have your original numerical solution at those points. The original one, when the spacing is delta, is only calculated at the circles. So only calculate the Richardson extrapolate at the circles as well, and then you'll calculate the global error and plot it versus that delta. So just to summarize, let's just make sure you understand. The first time through the loop, delta will be equal to h. But you will need to get two solutions. One with delta equal to h, and another one with delta equals h over 2. You will take those two solutions and calculate the Richardson extrapolate solution using this formula. But when you do that, you will only calculate the Richardson extrapolate at those points in the mesh with spacing delta. Not in the mesh with spacing delta over 2, but only in the mesh with spacing delta. So you will calculate the Richardson extrapolate at that, on those nodes, and then you will calculate your global error, and you will record that global error for that delta. And now you finish and you go to the next turn through the loop. The next time through the loop, you'll have delta equals h over 2, but you will need to get two solutions. This time the first solution will be delta equals h over 2, and the second solution will be delta equals h over 4. You will use this same formula right here to calculate the Richardson extrapolate on the mesh with delta equals h over 2, and again you'll find the global error. And do this for enough times through the loop so that you can get a reasonable plot of the global error versus delta and the log of the global error versus the log of delta. And you should see something quite interesting when you do this. So that concludes part 2, and so altogether then we have 2 parts in this project 3, and in each part you want to be producing 2 graphs. And so that concludes lecture 5, and good luck.